All right, Linda, I want to start out today's show with a definition. I'm just actually curious if you know this word, because I only know it from reading NLP stuff. I've never heard it outside of that context. Do you know what a corpus is, plural corpora?
How do you spell it?
Corpus, corpus.
But could it mean a body?
Well, why did you guess that? That's sort of right. But why?
I'm not a guess, it's Latin.
Oh, I didn't know you did Latin.
I didn't. Corp?
Oh, okay. Oh, maybe that's how corpse comes from. Well,
Yeah.
anyway, yeah, so corpus, at least in the context I know it, means a collection of documents. So it's specific to, these are, it could be tax forms, or it could be essays that students have written, or medical conversations. But a corpus is some just raw text collection of documents. Does that make sense?
Yes.
Now, the reason natural language people are interested in corpus, or why we talk about it, is because often we want a really large sample of documents to do some processing on, whether that's some sort of thing like we want to help people with grammar, and we want to just kind of do that statistically by studying the patterns of when certain words are used, or we want to study those documents, put them in, what the topic is, or any of these, general natural language tasks that we might be interested in, many of which we'll cover on the show this under this theme. To do much research, you have to have a good corpus.
So a body is kind of a body of research papers? Is that what you said?
Well, that could be an example of a corpus, sure. But it could also be something general, like all of the tweets from 2018.
All of the tweets. Well, I mean, what you're saying is in order to have good research, you just need to have good resources. So, yes.
Yeah, you need a big data set to work on. And we're going to actually talk more in a moment about just how big it should be, but I wanted to give a couple other famous examples. People who want to go deeper into this should look up the Brown corpus. That's an old, very old one at this point. I worked on that when I was still in school. I did some stuff with the switchboard corpus, and there's certainly more modern things, but those are the start of the trail if you're looking for some corpora to work with. And there's one famous one I wanted to make sure we got a mention of. You remember where we were for NIPS?
NIPS, Montreal.
In case listeners haven't been there, can you tell us a little bit about the bilingual nature of the place?
Montreal is in Quebec, so their first language is French, and English is used, but not as much.
Yeah, and I mean, compare it maybe to, we've also been to Berlin, where I would call that a bilingual city, speaking German and English. French is to Montreal is, well, sorry, I don't know the analogy, but can you compare and contrast those two cities in this context?
I think the analogy you're trying to make is French is to Montreal as German is to Berlin.
Yeah, but are they on par with one another, would you say?
That I don't know, as I don't know as much about the education system in both. But the menu in Montreal usually comes in French, and not every restaurant has it in English.
Yeah. Well, I guess my, single anecdotal perspective, the point I'm trying to drive at is that I thought that Montreal was way more French than Berlin was German. Anyway, I think some of that shows up in the laws. Apparently they have some law that every government document, or maybe it's just the transcripts of parliament, they have to be recorded in both English and French. And this has proved to be an amazing resource for a lot of translation research, because now you have this wide body of things that are translated very accurately. So you have, an A and a B version, and all you have to ask the machine to do is learn the mapping from one to the other. Pretty neat, huh?
Interesting. It is odd to have the law in two languages. If you're trying to dispute the law, I wonder how that shows up in court.
Yeah, I don't know exactly, but it's, clearly they're very much in support of keeping that part of the culture and tradition, a forefront enough to pass a law like that, which is kind of cool. And it's given us the side benefit that we have researchers in translation have this nice little pre-built corpus for them.
Yeah, how far back does it go?
That I don't know the details on. And to be perfectly frank, I don't think that corpus is as important today, as it was back then. I think a lot's changed in NLP and in translation, but it's still going on, and I am sure it's still a useful resource to many people.
All right.
Now let's go a little bit further back in time, all the way back to 1960, and I want to talk about a paper called The Unreasonable Effectiveness of Mathematics in the Natural Science by Eugene Wigner. This is a cool paper where he talks about a lot of the ways in which it's surprising how mathematical nature is. Do you know what that kind of means, and do you have a reaction to it?
Well, I didn't read the book, but I mean, I think the most obvious one is, like a flower, how the petals are so evenly spaced,
Oh, good example.
or
Yeah.
leaves, how they are either alternating or equal distance from each other. And then just generally in nature, there's a lot of symmetry, like in a butterfly.
Yeah, excellent points. I myself would have gone more the physics route and just talked about how gravity is so precisely mathematical and Maxwell's equations are. And, you get quickly into this sort of mathematical Platonism area where things are very regimentedly mathematical at the quantum level and whatnot.
Yes.
So,
Well, I am a visual learner, so my examples were visual.
yeah, mathematics clearly a powerful descriptor of nature. And because that was such an important paper, people have been spinning off and kind of referencing, that idea and coming up with other unreasonably effective da-da-das, including a paper that came out called The Unreasonable Effectiveness of Data that came out of Google research. And in that paper, they talk about a similar idea with how effective data is at just scaling. The more you have, the same sort of simple algorithms do a great job. That in many, the secret to solving a lot of problems isn't having smarter algorithms, it's having better data. Does that surprise you?
No. I mean, that's the crux of a lot of issue, right? Sometimes we want the answer to something, but we just don't have any data or haven't done any research. And then when you look at the research or data, your takeaways or learnings or whatever you decide are only as good as your data.
The idea actually goes even further. There's this very influential paper. It was someone I was very fortunate, someone pointed me to this in grad school, and it had a big impact on me. The paper's titled Scaling to Very Very Large Corpora for Natural Language Disambiguation. It's by Banco and Brill at Microsoft Research. They were looking at algorithms that they were working on for tense disambiguation, like the there, and
Mhm.
there kind of
Mhm.
problem, and which one goes there, goes there. And they looked at a couple of different algorithms that you could use to train it. One is people will know it's the naive Bayes that we've talked about. People also know the perceptron. And then there were two others, one called the Winnow method. I can't remember how that one works. And then there was something called memory based, which also I don't recall the details of. But these are just, different algorithms for trying to learn patterns in the data, pretty typical machine learning stuff. I guess at the time they started working on these problems, they had like a 500,000 documents to look at. So basically, their corpus was a bunch of like news articles or something like that, and they could find in each of those, well, where does the word there, and there appear, and then look at like what words come before it, and what words come after, and that kind of stuff, and hopefully learn the pattern. What do you think of that style of learning? That's not exactly how you learned grammar.
Well, I don't know. What are they trying to accomplish?
Oh, yeah. So they would like to have those algorithms be able to predict whether or not in a new sentence the correct form of there was used. And, if it's not, presumably like in some word processor, it could flag it and say,
Mhm.
hey, this is the wrong
I
word.
mean, and you're saying they just looked at documents to see how they used it?
Yeah, they had a very large corpus of about 500,000 examples of here's how the various forms of there appear in different documents.
And where are these documents? What are they? And were they correct?
Oh, that's a really good question. Yeah. As I recall, they were news articles pulled from the web, but if I'm wrong about that, they're just, some articles. Maybe for the sake of argument, let's say they were encyclopedia articles and we can trust that the correct
Mhm.
grammar was used, something
Well,
along
then,
those lines.
I mean, it sounds fine. Why? Do you see any issues?
Well, it's just, this is something that some people will have contention with because they'll say, grammar is you have to study it, you have to know its rules. How can you just look at a blanket amount of data and somehow you figure out the rules without knowing them? You can just detect the right situation. I don't have a problem with that, but I was just curious to have your
I mean, I don't
perspective.
have a problem.
All right.
But I mean, I guess when you think about it, if that's your only goal to detect there, and there, that's fine. But if you actually wanted your algorithm to learn more in depth grammar, you'd probably teach it the overall grammar structure.
Ah, well, that's going to be a discussion for another day because there I think we can debate it. But that's not what this episode's about. All right, data skeptic listeners. Can you get to Orlando, Florida in March, specifically the 18th through the 21st? That's when the Gartner Data and Analytics Summit is taking place. And I want you to head to gartnerevents.com/dataskeptic to see if this is the right event for you. There you can go to why attend, learn about some of the details, and take advantage of their Convince Your Boss feature. Because hey, is your boss sending you to conferences? They probably should. Continuing education is critical for a data professional. After you're done with why attend, go ahead and look at some of the tracks that are going on. You've got 8 tracks to choose from. I've already featured data science and machine learning on a previous episode. Let's talk about leadership in organizations and leading with a purpose. There are great workshops like Data Analytics is a Team Sport, so how do we get your team to be the top of the league? And sessions like So You Want to Be a CDO, for those of you who are aspiring to a Chief Data Officer role, and a wide range of other options. At the Gartner Data and Analytics Summit 2019, they'll help you take data from analytics to the next level. Join more than 3,000 data and analytics leaders discussing topics like AI, machine learning, IoT, digital twins, data science, advanced data analytics, pervasive analytics, and data governance. Find out more at gartnerevents.com/dataskeptic. Once again, that's taking place in Orlando, Florida, March 18th through 21st, gartnerevents.com/dataskeptic. This episode is about these very, very large corpora. The interesting thing that Banco and Brill did in this paper is they, like I said, they started with 500,000 documents. And I think probably because when they were working on this, obviously it's a long time ago at this point. So computers were small, memory was expensive, and there were maxes to it. So they were limited by the technology in a certain way. And then they revisited this problem when they were able to process 1 billion documents, whether that's because they had more space or faster machines or just had collected more documents. I don't know the details, but basically they had access to this 20 times larger corpus. So they had already run these 4 algorithms I mentioned on the 500,000 corpus, and they could rank them, who was in first, second, third, fourth place. And when they went from 500,000 to 1 billion documents, here's the really interesting part. Fourth place moved to first place, third moved up to second, 2 went down to 3, and 1 went to 4. The exact reverse order. Same algorithms, all they did was give it more documents.
So when you say the first and the third, first place of what?
So the algorithm which had the highest accuracy.
Are you saying there are multiple algorithms that they were competing? How many were there?
4 algorithms.
And what's different between them?
Well, that's a big discussion because I have to explain each of them, but let's just call them different techniques. So the perceptron, for example, is one of the classic elements of a neural network, and it has this sort of linear sum and activation. Naive Bayes, on the other hand, follows Bayes' law very closely, and it's a pretty statistical sort of a method. So they're just different techniques for how you might decide which of the words is the right one to fit.
Okay, so then
Different algorithms.
What's your question?
Well, I wonder, I didn't actually ask one, I don't think. I was just curious if
okay.
you had any reaction, because this is a profound reaction for me, that the first place, when competing with only 500,000 documents, you would celebrate, be like, hey, that's the best algorithm, give those guys a prize. Well, when you give it more data, first place has dropped to fourth, and fourth has gone to first. They've switched orders. The algorithms didn't change. The data just got more plentiful.
So the first test, how many cases did the first test have?
500,000.
And then the second test had how many?
1 billion.
Oh, 1 billion.
Yeah.
So you're saying they went in reverse order when they tested 1 billion?
Yeah.
I don't know. What's the answer?
Well, I mean, the key observation for me, there's a couple of them, is one is having a fancy algorithm is not necessarily always going to win the day. And there could be certain areas where, with not very many documents, you could have some clever algorithm that squeaks ahead because a little bit of wisdom is baked into the, some implementation detail its creators came up with, or they hard coded something or overfit something. But as you look to the horizon, if you can just keep giving it more and more documents and you see asymptotically how the performance in terms of how accurate they are, each of these things turns out to be, everybody's probably going to improve with more documents, but some people might be some algorithms might be slow starters. So they look like they're performing very poorly if you have a small corpus, but suddenly you have a large corpus, they're the obvious winner. Neat.
But why is that?
Well, I think the moral here is that a simple algorithm isn't necessarily a bad thing. Maybe you just need to train it sufficiently well enough and given enough data, enough examples that systems are able to rather trivially learn things that we think are complicated.
But here's my question. When you say the accuracy, how big of a difference between their accuracy? Like one's like 99, one's 98, 197% accuracy? I mean, if they're not even that big of a difference. Because I feel like if you just rank them, it sounds like a big deal. But if you actually look at the data, it may not even be that big of a deal.
Yes, I'm pulling that up now. At the 500,000 mark, let's just talk about first and fourth place. So their memory-based method looks like about 83% accurate, and that got first place. Also in the 500,000 documents category, the winnowing algorithm in last place at about 75% accuracy. So there's a 8 percentage point spread. When we jump out to 1 billion documents, as I said, they've switched orders. Winnowing algorithm is now winning at, a little hard to read from this chart, but I would say 97% accuracy. And memory based has dropped to fourth place at, again, eyeballing it, about 94% accuracy.
That's
So here we have a tighter, only 3-point spread,
yeah.
but that's significant.
Yeah, I mean, it's significant for 1 billion.
Yep.
So the accuracy went up significantly, though. So did they make improvements?
Not to the algorithms, no. Same algorithm, more data.
And that's normal?
Well, it obviously depends on the problem. If you're measuring something very, very simple, then you don't need that many examples. But for all of the kind of interesting problems that you would even think machine learning are appropriate for, this seems to be a common pattern. Train on more images, you get better image recognition. Train on more chess games, you get better chess players.
So just more means more accuracy
Yeah.
on average. Are there cases when that's not the case?
Well, for sure. Like, let's say you were going to try and use machine learning on some physics experiment, and the parameters are just like temperature, pressure, displacement, this kind of stuff. Those are obeying some very simple physical law. So they're going to do the same thing every time, plus or minus the natural variance of the system. But compare that's kind of like saying, you flip a coin, it's going to be 50-50. Like, machine learning is not going to predict very well. But compare that to an election that you could think of as almost 50-50 with two candidates, but the reasons why every person voted the way they did are super complicated. Everyone's their own individual. So it's, there's so much more variance in the voting example.
Okay.
And there's one last thing I wanted to get to, just because this is going to come up in some of our episodes coming up quick, is something called Zipf's law. It falls in line with this large corpora discussion. Zipf's law basically describes how often you'll see something. So let me just give you the stats and then we'll back up to the definition. In most corpuses, I'm going to quote the Brown corpus in particular, the most frequent word, guess what it is? What's the most frequent word in a particular English document?
In a particular?
Yeah.
What's the document?
Any document, just a random document, a random website. What's the most common word?
The.
You got it. 7% of the words are the in the Brown corpus. Guess number 2. What comes after the? This is hard.
I don't know. Is it like is?
No, good guess though. It's of, followed by third place, and.
And oh.
Yeah. And so, like I said, the is 7% of the words, is 3.5, and is 2.8. And it kind of trails off in this exponential decline. Basically, Zipf's law states that the frequency of any word in a corpus is inversely proportional to its rank in the frequency table. So the frequency table is just the data ordered, sort from most frequent to least frequent descending. And if you're on the first row, second row, third row, that's your rank, and inversely proportional to that, so it drops off pretty quick. Zipf's law also applies to things like the population of cities. If you look at the size of New York, followed by LA, followed by Chicago, and what's fourth? Houston, maybe?
I don't know.
Yeah, I don't know either. And also works on income and even podcast popularity based on the download statistics I get from the Libsyn Corporation. Lots of things follow this distribution, and it comes up in a couple of places in some episodes we have coming up. The last interesting thing about Zipf's distribution is it happens, and this I wouldn't have necessarily predicted, but it happens in all known natural languages and even some unnatural languages like Esperanto. That even though the most common word is not the in another language, their the followed by their of and their and, or whatever their most popular words are, they follow the exact same pattern.
What do you mean? What's the pattern?
That the most popular word will be maybe around 7%. The second most popular will be half of that, and we'll have this kind of declining relationship.
What other languages are these like programming languages?
No, natural languages.
What are natural languages?
Korean, French, German, Italian. Latin
So
even.
they've examined all of them
Yes.
in the world, or at least the top 20.
Yeah, I think that's safe. Yeah, top 20 for sure. I mean, there might be some weird language that no one has happened to check this on yet, but yeah, pretty much every language does this.
Really? Hmm.
Yeah, yeah. Well, I'm not that surprised by it. What surprises you?
I don't know. I kind of view those words. I'm not a grammar person, so I don't have the right
Hmm.
words, but I feel like those words are like connector words. And I feel like some languages have less of them.
Oh, interesting. Yeah.
So I just don't understand. That doesn't seem right.
It's not necessarily that the connector words show up, although they probably have some semblance of a connector word, but whatever their most popular word is, followed by the second most and the third most popular word, they're going to follow the same trend. It doesn't have to be that they're all connector words. Although, I mean, I would imagine they are
I'd be interested to know what those words are, and what they are
in
across
other
the languages
languages.
and how that impacts the way that language is structured.
Ooh, that's interesting. Yeah. You could probably do that pretty quick in NLT Kay if you put your mind to it. That's this Python library that also has some built in ways to get some corpuses downloaded for yourself. I imagine there's a way to get other languages and you could compute Zipf slaw pretty quick. If anybody does that, let me know and we'll talk about it on the show.
Yeah. I want to hear the results.
Well, anyway, do you think you have a better understanding of what corpora are and why they're important?
Well, yeah. I mean, it seems obvious that it's important. Why are you bringing it up on your show, though?
Well, because we're still early on in our natural language processing series, and I need to emphasize the importance of corpora, how useful they are for training. Really want to emphasize that result that sometimes more documents are what you need, not better algorithms, and then get the mention in for Zipf's law.
But it doesn't this apply to like any of the data skeptic themes?
This large corpora stuff doesn't necessarily know because let's say you were like trying to use machine learning to predict customer churn or something like that, even though I think that's not a very fruitful activity. No matter how big of a company you are, you're only going to get a limited, couple of million. I guess it gets kind of big, but for a lot of things you want to do machine learning on, you're not going to have access to extremely large corpora.
Oh, so then you're saying you just have to work within the limitations.
Sometimes, yeah.
But with NLP, you're saying the assumption is that corpora exists.
Well, yeah, and that you're obviously training on some corpus, and the bigger it gets, the more effective your learning is going to be. And that's not exclusively natural language. That crosses into pretty much anything you would throw deep learning at. That'll work on, speech signal processing kind of stuff. I'm sure it'll work on image recognition and translation and all those sorts of things too.
Do you think that's how the human brain works?
That's a very good question. I think so because I think we underrate how much training time that goes on in our brains. I mean, let's face it, human beings are pretty useless for several years. As far as like they can't be on their own or anything like that. And even as like little babies, they're learning. They seem to be learning very quickly, just like motor skills. They weren't born with that stuff. So every day is another 24 hours or however long you're up, another big chunk of new training data. So I do think, yes, we benefit highly from these unreasonably effective large training data sets, which is just our childhoods.
Which is what you're saying that's life.
Yeah, I guess. Is that the new T-shirt? Data skeptic, that's life.
No, I was saying the large corpora. Yeah.
Yeah, that one's life is an extremely large corpora or corpus, because that would be one
Corpus.
collection.
Okay.
Yeah. Well, corpus specific to documents, but data sets, large data sets, seem to have this very nice property. So yeah, it's not always, hey, go learn the latest algorithm. It's sometimes, how are we going to build up the infrastructure to process the large thing?
Okay, interesting.
Well, I think we hit on all the high points. Thanks as always for joining me, Linda.
Thank you, Kyle.